So let's talk about some problem-solving strategies we can use when given a proton NMR. How can you go about determining a structure from it? Three basic things we need to accomplish are: first, determine what pieces are present. Okay, what we're going to be doing is very much like building a puzzle. And so the first thing we have to do is figure out what puzzle pieces there are. Then we have to figure out how to put those pieces together. And when we're done and we have a structure that we'd like to propose as an answer, what we're going to do is we're going to confirm that the structure does in fact match the spectrum. We're going to use those skills that we did in being able to predict an NMR spectrum given a structure and confirm it. So what's great about NMR is when you have the right answer, you know you have the right answer, and you can breathe a sigh of relief and move on. Okay, so here are the steps we're going to take. The very first thing we need to do is, if we're lucky enough to have an IR spectrum provided to us for our molecule, then we're going to analyze that spectrum for any functional groups that might be present. Okay, a lot of times spectroscopy problems are given in combination, so you'll get maybe an IR spectrum and a proton and a carbon NMR. And so the more data you're given, great, work with it. So let's take a look at the IR, see if we have things like, a carbonyl is really obvious in the IR, somewhere around 1700. We find that very strong signal. OH groups are very obvious in the IR, those broad peaks around 3300. Right, we can look for the presence of double bonds, hydrogens on those triple bonds, and so on. Okay, so those are going to be pieces to our puzzle. Those have to be incorporated into our final answer, into the structure that we have. Okay, the next thing we're going to do is we're going to look at our molecular formula. If it's provided, if we're lucky enough to have our molecular formula, we're going to analyze that and determine how many degrees of unsaturation we have. Now what we're going to do is we're going to look for the formula. C to the n, H to the 2n plus 2 is the formula we expect if we have a saturated molecule. If we have any nitrogens present, we need to account for those by for every one nitrogen, we need one extra hydrogen in our structure, so we can modify our formula a little bit to accommodate those. Oh, I'm sorry, 2n plus 2. See that I missed my n there. So twice the number of hydrogens plus 2. Okay, and every two missing hydrogens gives us a clue to our structure, because it tells us we have a degree of unsaturation. That means we must have a double bond, or we must have a ring to account for those missing two hydrogens. Okay? If we happen to have 4 or more degrees of unsaturation, then it might be possible a structure as a benzene ring. If you take a look at a benzene ring, we have a 6-membered ring with alternating pi bonds. Okay, so that means we have 3 pi bonds plus 1 ring. That equals 4 degrees of unsaturation. That means if we have 8 missing hydrogens, then it's possible that we have a benzene ring in our structure. That's a great way to account for a lot of degrees of unsaturation very quickly. If we do not have 4 degrees of unsaturation, if we have fewer than that, it's impossible to have a benzene ring in our structure. So really, the molecular formula is telling us something very significant about our structure. Okay, the next thing we're going to do is we're going to draw out the various pieces to our molecule. We're going to be using the peak integration, the size of each peak, to tell us how many hydrogens there are in each. Okay, so for example, if you see a signal that has 3 hydrogens in it, let's assume that's a CH3. Okay, because it's possible to have 3 hydrogens coinciding some other way other than a methyl group. But if you hear off in the distance, if you hear something galloping, you hear hooves beating against the ground, you should probably think in terms of horses before you imagine that they're zebras. It's possible that they're zebras, but let's go with the more obvious choice, the more likely choice. Okay, so a 3 hydrogen signal means we probably have a CH3. A 2 hydrogen signal means we have a CH2. A 1 hydrogen signal means we have a CH, or maybe an OH or an NH if we have those elements in our formula. Okay, a 4 hydrogen signal is a little trickier, not as common, but obviously there's not a CH4 puzzle piece. So maybe we have 2 CH2s, that are chemically equivalent, therefore giving rise to 1 signal, or maybe a CH3 and a CH that can't be chemically equivalent, but they might just be overlapping because they have the same chemical shift. So there may be some more complex things, but we'll come across that. We'll deal with those when we come across them. If we have peaks around 7 parts per million, we're going to assume there's an aromatic ring, a benzene ring. Okay, it might just be a single peak. Very common if they're very similar in their chemical environment, then they're going to have the same chemical shift. Or you might have several signals in the region around 7. Okay, we're going to look at all the signals that are around 7, and we're going to see how many total hydrogens there are. If we have 5 hydrogens around 7, that means we have a monosubstituted benzene ring. So in other words, the piece to our puzzle is a benzene ring with something attached. Okay, that means if you attach one thing, so we have a monosubstituted benzene ring, that means you have 1, 2, 3, 4, 5 hydrogens left, and those are going to show up in your NMR. Okay, if you have a total of 4 hydrogens around 7, that means you have a disubstituted benzene ring. So this is monosubstituted. Disubstituted means that you have a benzene ring with 2 things attached. You know, where are those 2 things attached? They could be para or ortho or meta or para, but you have only 4 aromatic protons, meaning 2 of those positions are occupied by something other than hydrogen. Okay, so we're going to do this to come up with all the pieces in our puzzle. And then the next thing we're going to do is we're going to confirm our pieces and make sure, before you start building your molecule and putting your pieces together, you better make sure you've come up with all the correct pieces. So what we're going to do is we're going to add them up, and we're going to make sure that they match the molecular formula. Okay, the way you can do that is to make sure, have you accounted for all the degrees of unsaturation? If you said there were 2 degrees of unsaturation, do you have 2 double bonds in your pieces? If not, know that you still have to incorporate a ring when you put those pieces together to get that second DU. Have you accounted for the functional groups in the IR? If the IR told you you had an OH, then one of the pieces in your puzzle needs to be an OH. Okay, so we're going to confirm that we have all the pieces present. Now we're ready to start putting them together. Okay, how do we decide which 2 pieces are connected? Well, we're going to consider the chemical shift. Is it electron rich, electron deficient? We're going to consider the splitting pattern. Does it have any neighbors? Okay, and we need to consider both of those. So the easiest thing is to start with an end piece, like a methyl group, and start to see what things we can attach to it. Okay, for example, if it's next to an oxygen, I could attach it to an oxygen if its chemical shift is around 3.5. Maybe it's next to a carbonyl or a benzene ring if its shift is chemical shift around 2.2. So we'll consider where it is on the spectrum to decide who it's next to. And we're also going to consider the splitting patterns. If it's a triplet, that means it must have 2 neighbors. So I'm going to find a CH2 piece and I'm going to attach it to that. Okay, so bit by bit, we're going to take all these different pieces and start hooking them together until we come up with a complete structure. Before we're done and we pat ourselves on the back, we need to go back and check our structure. This is the last step in our methodical process. Does it match the molecular formula? Sometimes when we start working, if we spend a long time on a spectrum, it's easy for a piece to fall off and never get added back on. And then you think you have the solution, you realize you're missing some carbons or oxygens or nitrogens. So does it match the molecular formula? Does it match the functional groups in the IR that you predicted? Does it match the NMR? Remember, we worked on how to predict an NMR spectrum. How many signals are you expecting? Is there the symmetry in the molecule that's required to get the right number of signals? What would the integration be for each peak? What would the splitting patterns be? What would the chemical shift be? Okay, so that's our very last step is to confirm that we have, in fact, determined the right structure. So let's try some problems. Okay, here we have a structure with the formula C9H10O2, and here's our NMR data. So instead of giving you a spectrum, it's presented to you, just in numerical form here. Okay, and the problem with NMR that I see again and again working on NMR problems is there's so much information, you could just get blown away by that information, and it's very easy to spend 30 minutes working on an NMR problem and go nowhere because you just are grabbing at bits and pieces. Okay, so we're going to develop a systematic approach. We're going to use that same approach every time, and we're going to hopefully find success in that approach. Okay, so what was our first step? Our first step is to look at the IR spectrum and see what we can figure out from that. But we're not going to be looking at any IRs today. A lot of the problems you're going to see in your courses or in the books will have IR combined with NMR, so that you're lucky in those cases, you get that as an additional clue of what functional groups you have. But in all these cases, we're going to be skipping the IR. Okay? Do we have a molecular formula? You won't always be given a molecular formula, but if you're lucky enough to get it, let's use it. So we do have a molecular formula. It's C9H10O2. What can that tell us about the structure? What we need to do is we need to calculate the DU. Okay, the way we calculate the DU is we ask ourselves, if it was saturated, what would the formula be? We have 9 carbons. It would be C9H to the, remember it was C to the N, H to the 2N plus 2. So it's 9 times 2 is 18, plus 2 is 20. If it was saturated, it would be C9H20. What do we have? We have C9H10. Okay, so what do we have? We have 10 missing hydrogens, and every 2 missing hydrogens is a degree of unsaturation or a site of unsaturation. So we have 5 DU. So our formula, when we're done, has to account for all 5 of those. Okay, now what do? We figure out what pieces we have to our puzzle. We use the integration for that. So we have 5 hydrogens here, somewhere around 7. What piece does that tell us? What thing's coming around 7? That would be aromatic protons. We have 5 of them, so that tells us that we have a monosubstituted benzene ring. We have a benzene ring with 1 something hanging off of it, attached to it. Okay? We have a 2 hydrogen signal. What does a 2 hydrogen signal mean? It means we have a CH2, and when I draw this piece, look what I'm going to do. I'm going to draw 2 arms on it. And that's because we know every carbon's going to have 4 bonds in our structures when we're done, because we're only looking at stable, stable structures. So a CH2 must be attached to 2 other things to get those 4 bonds. And what does a 3 hydrogen signal tell us? That means we have a CH3. A CH3 has just 1 arm, because that would be the 4th bond. So these are our pieces. Are they all of our pieces? Well, what do we have so far? We have C6, 7, 8. We have C8, H, 5, 6, 7, 8, 9, 10. Okay, so we've accounted for all of our hydrogens, of course, because they show up in the NMR. It's hard to miss those. But we only have 8 carbons shown, so we still have a carbon. We still have 2 oxygens that we need to account for. Oxygen has 2 arms, right? Oxygen likes to have 2 bonds. And what else are we missing? Let's check our formula. Our formula says we need 5 degrees of unsaturation. How many have we shown so far in these pieces? We've only shown a benzene ring, which has 1, 2, 3, 4 degrees of unsaturation. So we still have 1 degree of unsaturation that needs to be in our structure when we're done. Now this looks like a lot of random pieces, but take a look at this. There's actually a very nice functional group we can imagine that takes care of all 3 of those. What is a way to have a carbon and an oxygen with a degree of unsaturation? How about a carbonyl? A carbonyl would very nicely account for all 3 of those pieces in one nice, functional group that we see all the time. Carbonyls are very, very common in organic molecules. And of course, a carbonyl has 2 arms. Okay, so these now are our pieces. So we've taken care of this. So we have a phenyl ring, CH2, CH3, carbonyl, and an oxygen. Those are our pieces. Now we're ready to put them together. We start with an end piece, and we decide what it's attached to. So let's start with our CH3. What are our choices? We could either attach it, could we attach it to the benzene ring? We can't attach it to a benzene ring because that's an end piece. If we attached a methyl and a benzene, we would now have toluene, our structure would be done. We couldn't fit in any of the other groups. Okay? But I could attach it to a CH2 or an oxygen or a carbonyl. Those are the other possible pieces. How do I decide which one it belongs to? Well, now I take a look. Where's my CH3? I take a look. It must be a singlet. So what does that rule out if it's a singlet? Singlet means that I have 0 neighbors, right? I have 0 protons on my neighboring carbon. So I can't attach it to the CH2. That would split it. But it could be the oxygen or the carbonyl. How do I decide which one it is? Well, I take a look at the chemical shift. Is that the chemical shift I would expect when I'm next to an oxygen or when I'm alpha to a carbonyl? That means I'm alpha to a carbonyl. If I put it next to an oxygen, that brings me too far downfield, brings me closer to 4. So I must have this attached to the carbonyl. Okay, that took care of this piece. That took care of this piece. What comes next? What are my options? I can either have an oxygen or I can have a CH2. Okay, now it turns out in this case, let's take a look at that. Let's put the oxygen first and then the CH2. And then the last piece I would have is the benzene. Or the other possibility, we're down to just 2 possible structures. We could have the CH2 and then the oxygen. Okay, and we can use, would that explain the chemical shift and the splitting pattern for the CH2? It would actually, because this is a singlet, which is true in both cases. And it comes at around 5. How does it get all the way to 5? Well, it's both next to an oxygen and it's next to something else. In this case, a benzene ring. It's benzylic. In this case, next to a carbonyl. So actually, both of these answers are reasonable. The way I would distinguish between the two of them, if I had some tables, maybe I can calculate it a little more precisely to see which one best matches 5.1. But the other thing that I would recognize, it's a little more sophisticated, is I know that having an oxygen on a benzene ring is going to have some resonance, which is going to make some of these protons much different, give them a much different chemical environment, electronic environment, than the others. So because it is a 5-hydrogen singlet, I'm expecting all these hydrogens to be very similar and therefore just attached to a regular CH2, and so this is the best match. This is the best match. Occasionally we might have a case where there's more than one possible answer, but that's pretty. This is a pretty rare situation. Okay, let's try a different one. Turns out we have the same formula and we have the same pieces. So just like we did our process before, we would find that we have 5 degrees of unsaturation. So we have a 5-hydrogen aromatic signal. We have a CH3. We have a CH2. We have a carbonyl. And then we have an extra oxygen. Same 5 pieces as we did in the previous problem. How are we going to put them together? Well, again, let's start with our methyl group. Let's start with this end group. Tell me about this methyl group. It's a singlet again, so it has the same splitting pattern as before, but now it's at 3.6 ppm. So which piece would make sense to attach to the methyl that would bring it to 3.6? This would bring it to 3.6 if we put an oxygen next to it. Okay, so that takes care of our oxygen and takes care of our methyl. What do we have next? Or what other pieces can we put together? Well, let's think about our CH2. What is our CH2 going to be attached to? Our CH2 is at 3.5. Okay? So if we put, let's think about our possibilities. If we put that here, if we put our CH2 next, we would expect that to be at 3.5, just like the first one. But then when we attached it to another piece, the carbonyl or the benzene ring, what would happen to that 3.5? That would de-shield it even more, and we wouldn't expect it to be there any longer. So we can't put the CH2 here. Instead, it's the carbonyl and then the CH2. So don't be afraid to look at your options. Rather than have it all swirling around in your head and trying to imagine all the possibilities, just write out the 2 possibilities that you're considering and then see which one fits the data best. Okay? Right? So what I'm saying here is if this were the carbonyl, if we looked at this option, then this would be much more downfield. This must be higher than 3.5. Okay, but now if we were to predict this, where do we expect this to be? Well, it's going to shift a little downfield because of the carbonyl, and it's going to shift a little downfield because of the benzene ring, that would put it at 3.5. 3.5 ppms is very reasonable for this one. We would expect it to be a 2 hydrogen peak. Is this a singlet? It is a singlet, just like we predicted. I went through this a little bit on the previous one, but we want to make sure that we double check our work. This CH3, what do you predict for that? Its splitting pattern would also be a singlet. And where do you expect it to occur? What would its chemical shift be? It's attached to an oxygen. So again, 3.8 we would expect here. It's 3.6. That makes perfect sense. These hydrogens all are our 5 hydrogens around 7. In this case, 7.4. Okay, so we can propose a structure and then double check it, and we know we have the right answer. Okay, let's try a different molecule, a little more. Now we have some spectral data here. Okay, because we have no IR information, let's go straight to the chemical formula, C10H14. What do we know about C10H14? Let's check whether there's any degrees of unsaturation. So here's the question we ask. Rather than doing some kind of formula to randomly come up with an answer, magically come up with an answer for degrees of unsaturation, it's much more reliable to just kind of think about it in terms of, well, if it was saturated, what would the formula be? If it was saturated with 10 carbons, how many hydrogens can possibly fit on 10 carbons? 2n plus 2, 20 plus 2. So it would be C10H22 if it was saturated. So when we compare the actual formula to the saturated formula, we have 6, 7, 8. We have 8 hydrogens missing. And how does that translate to degrees of unsaturation? Every 2 missing hydrogens tells us we have a double bond or we have a ring. We have a DU. So there's 4 DU in our structure. Okay, that's a very important clue. It's going to help us determine what our pieces are. Okay, so then the next thing we do is we look at our peaks and we decide what our pieces are based on the integration. Okay, and here rather than the integral trails, they're just giving you the number of protons. So we can start anywhere. 6 hydrogens. How would we get 6 hydrogens? Can't be a CH6. What do we have? What would be the most likely thing we can have here? Probably a CH3 and another CH3 that are equivalent and therefore giving rise to a single signal. Okay, so 2 CH3s, a 3 hydrogen signal here means that we have a CH3. Another CH3, a 1 hydrogen signal means we have a CH. Now a CH has 3 arms, right, to come up with 4 total bonds. How do I know it's not an NH or an OH? Because I only have carbons and hydrogens. I just have an alkane, a hydrocarbon with my formula. So it must be a CH. And then what do we have over here? We have 4 hydrogens, and they're around 7. So what does that tell you? Probably have a benzene ring. How do we make a benzene ring with only 4 hydrogens on it? It means that we have 2. There's 6 hydrogens to start with on benzene, so we must have 2 of those hydrogens replaced by something else. So this is another piece to our puzzle, is having 2 groups. Now, do I know that they're para to each other? No. They could be para, they could be meta, they could be ortho, but we'll just pick one pattern to start, and then when we're done, we'll confirm to see if that seems like a reasonable substitution pattern. Okay, so those are our pieces. Let's double check before we start putting things together. Make sure we've accounted for everything. Do we have C10H14? We know we have H14 because we did the 6 and 3 and 1 and 4. We have all the right number of hydrogens, and we have 6, 7, 8, 9, 10 hydrogens. Okay, so we've confirmed with our formula. We have all the right pieces. Now we can start to put them together. Okay, it's best if you start with an N piece. Okay, and we have several. We have these CH3s, we have this CH3, and we can decide how to attach them. Let's take a look at this signal. It has 6 hydrogens total, and how would you describe that signal? What's the splitting pattern? It has 2 peaks. If you look all the way up the top, sometimes it's a little easier to see what kind of shape it is, in fact. And this is a doublet. And so what does it tell you about how many neighbors we have? It means there is one neighbor. So which piece can I attach it to that would give rise to that splitting? Well, I could attach it to this CH. If I attach this CH to two CH3s, if I put both CH3s on that, would that account for the signal I see? It does, because now these would be equivalent, because I could rotate around and those would be chemically equivalent, and that would be a 6-hydrogen signal. That's a doublet. So what I've done is I've taken these and these little pieces and connected them to be a bigger piece, a larger piece. Okay, what pieces can I connect next? How many options do I have? This is an end piece. This is an end piece. They each have just one arm, and then I have this benzene ring with two arms. So what can I do? I just connect them all. I put the methyl on one side, and I put the isopropyl on the other side. This is a CH with a CH3 and a CH3. And now I've put all my pieces together. Okay, let's see if it makes sense. Let's predict if that makes sense. What do you expect this peak to look like? It should be a 3-hydrogen signal. What should the chemical shift in the splitting pattern be? How many neighbors does it have? It has no neighbors, so this should be a singlet. And what chemical shift do we expect for being next to a benzene ring? About 2.2. And where is it? There it is, 2.4 maybe, somewhere around there. So that's good. If you want, you could label your peaks. This is A and this is A. That would be a very great way to check your work at the end and demonstrate that you really know for sure that this structure matches the spectrum. Okay, we said these methyl groups were together. We already analyzed that to make sure that makes sense. That would be signal B, let's say. We said it's a 6-hydrogen signal. That would be a doublet because it has one neighbor. How about this guy? Let's call this type C. And what do you expect for that? For that signal, it should be 1 hydrogen. And how many neighbors does it have? It has 6 neighbors, 3 plus 3. So we expect that to be a septet. And it's kind of hard to see that, so we've blown it up here. This is kind of common to see smaller peaks blown up and expanded. And what do we have? 1, 2, 3, 4, 5, 6, 7 peaks. There it is. It's a septet. So we must have 6 plus n plus 1. We must have 6 neighbors. So, so that makes sense to be peak C. Chemical shift, where do you expect it? Well, it's benzylic, so that's 2.2. It's also a CH. That brings it a little further downfield as well. So, you know, 2.8 is not unreasonable for that, where it was. That makes sense. And then finally, these 4 hydrogens. Looks like, what do we have here? It's kind of tough to see, but it looks like we have a doublet right next to another doublet. And because they're coupling with each other, because they are splitting each other, a lot of times we'll see the doublet kind of leaning, skewing toward this other signal that it's splitting with. And so that's why we have these really high peaks on the outside and these really short peaks on the inside. They're just slightly different chemical shifts that they're being resolved into 2 separate signals. But a lot of times, if this were a less sensitive instrument, this would just show up as our typical, you know, just singlet in this region. But should we expect 2 signals? Well, yeah, this hydrogen is different from this hydrogen. So we could call, we're at C, so we could call one of these D and one of these E. This is E and this is D. So we have 2 hydrogen type D. These are doublets. I don't want to confuse my D with my D for doublet with hydrogen D. So this is hydrogen D and E, and they're both, we have 2 doublets here. So if we wanted to, you know, narrow it down a little, this symmetry would explain that that splitting pattern and the characteristics of that shape. So that does look fine. Okay. Let's try another one. Okay, here we have, again, let's start with our formula, C4H8O2. When we're doing our degrees of unsaturation, we ignore the oxygen So we ask if it was saturated, our formula would be C4H2N is 8 plus 2 is 10. Our actual formula is C4H8. We ignore the oxygens because they have no impact on our degrees of unsaturation. And so we find that we have just 2 hydrogens missing. And that means we have 1 degree of unsaturation. So we need to account for that in our puzzle pieces. Okay, so let's figure out what pieces we have. We have we can start anywhere. We have a 1 hydrogen signal here, so we have a CH with 3 other bonds. We have a 2 hydrogen signal is a CH2. We have another 2 hydrogen signal that's blown up here to see a little more detail, but we have another 2 hydrogen signal that's another CH2, and then we have a 3 hydrogen signal that's a CH3. Okay, so those are some of our pieces. Are those all of our pieces? Well, we haven't accounted for our degree of unsaturation yet. We also have 2 oxygens. Okay, so is there anything we can do to consolidate some of these pieces into something recognizable? Well, this hydrogen is kind of unique. Having a hydrogen, a proton, resonate all the way out at 8 is a very, very far down field signal. And we've only seen a few of those. A carboxylic acid would come this far, an OH, or an aldehyde, CH. So a carboxylic acid comes even further, usually higher than 10. So about 8 is where we expect our aldehydes. So guess what? If I take this CH and attach them to the carbon as a carbonyl, then that would be a very reasonable puzzle piece that's consistent with all our data. This would be a singlet at, in this case 8, 9, could be even 9 or 10. And ppm. And the carbonyl gives us one of our oxygens and accounts for our degrees of unsaturation. Okay, so I think this is a reasonable puzzle piece to have. We still have a second oxygen, and then we have these, the CH2, CH2, and CH3. So we have 1, 2, 3, 4 carbons. We have 3, 4, 5, 6, 7, 8 hydrogens, and 2 oxygens. Okay, you absolutely have to double check before you start putting things together and jumping all over the place. If you don't have the right puzzle pieces, you cannot get the right answer. Okay, so this is a really important step we don't want to skip. Okay, now we're ready to put them together. So where's a good place to start? Really the only place we can start is with this methyl group, because that's an N piece and we have to figure out who it's attached to. So tell me about that methyl. It's up here way at 1, very close to 1, and it's a triplet. It has 1, 2, 3 peaks. See this 1 to 2 to 1 shape? That's very typical that we see for a triplet. So what does that tell you it's attached to? What are your choices? It could be attached to an oxygen or a CH2. Those are only choices. I can't attach it to the carbonyl because that's taking my 2 N pieces and connecting them, and I leave out everything else. So it must be attached to one of the CH2s. Why not an oxygen? What would that do? Well, 2 problems with that. They would make it a singlet, and it would bring it all the way down to 4 or so. So this is now consistent. Okay, so I used a methyl group, I used my other CH2. Okay, now I have a CH2, and it we can see where that goes, or we can kind of look at another point of view. We have these 2 CH2s. I don't know yet which is which. I don't know if this is the one, if it's this one or this one. So let's take a look at that. It has how many neighbors? It has these 3 neighbors. So it's going to be a quartet. This one is only a triplet. So this can't be this CH2 because it doesn't have a big enough splitting pattern. So let's just label this. If this is A, and then this CH2 is B, it must be this because it has at least 3 neighbors. What gives it this much splitting? Let's take a look at it. It has 1, 2, 3, 4, 5, 6 peaks. 6 peaks means it has 5 neighbors. So instead of, in addition to these 3 neighbors, it also has another 2 neighbors. We must have the other CH2 on the other side. Okay? even though these 3 hydrogens are not exactly equivalent to these 2 hydrogens, their relationship their spatial relationship to protons B here are similar enough that they have the same splitting constant, the same coupling constant, and so we end up with this very nice signal with like it has 5 neighbors all of one type. Okay, so that is, this must be proton C here. That's the other CH2 signal. Now tell me about this CH2 signal. It's a triplet, and it's up here at 4.2. What does that tell you that it's attached to? If it's all the way down at 4, that means it must be attached to the oxygen. So now I attach my oxygen, and then I only have one piece left, my carbonyl. So bit by bit, I attach it. Sometimes we can keep working linearly. Sometimes we group things. You could take a look at this CH2. You know it's a CH2. And you could say, you know what, he's all the way at 4, so I know he's attached to an oxygen. So you can start to group your pieces that way. Or you can group them you know, in a different fashion. So when it comes to putting the pieces together, that one is a little more individualistic on how you're going to solve it versus someone else. Okay, but the key is start at an endpoint, like with a methyl group, and see who it's attached to. Slowly start to bring your scattered pieces into larger pieces, and then see how those larger pieces can finally come together into a complete molecule. There will not be 1,000 choices. It might feel like the possibilities are endless, but there's really a finite number of choices. And so sometimes you come down to just a couple choices, draw them out, and see which one works, okay? Try and be as systematic and keep moving forward as best you can. Okay, does all the data match? If we were to look at this structure and confirm that it matches the NMR, do we have an aldehyde proton in our NMR? We do, up here at 8, so let's call that proton type D. That aldehydes are always singlets because they're always attached to a carbonyl. So we expect that somewhere really far downfield. What do you expect for this carbon? Now cover up the NMR. Don't look at the NMR at all. Look at your structure and predict it. Okay, if you're doing it while you're looking at the NMR, you can miss things, you can confirm things, you can lose sight of some evidence. So let's predict this. What do you expect this signal to look like? What's its splitting pattern? How many neighbors does it have? It has 2 neighbors right here, so n+1, we expect this to be a triplet. Where do you expect it to show up? It's next to an oxygen, so that's 3.8. In fact, in this case, it's 4.2. That's certainly consistent, certainly reasonable. That makes sense. Okay, what do you expect for B? Where do you expect it to show up? Or what's the splitting pattern first? We can do that. It has 3, 4, 5 neighbors, so we expect this to be a sextet. And it is, in fact, 1, 2, 3, 4, 5, 6. Where do you expect to have it? Nowhere special. It's just got alkyl groups on either side, so you know, somewhere around 1 as we expect. Why is it up here all the way closer to 2? Well, because not too far away it has an oxygen. So that does have some effect, but you know, as usual, these inductive effects decrease with distance. So it's not as much as if it was directly attached to an oxygen, but the presence of that oxygen brings it down a little bit. So yeah, 1.8 is fine for that. And this last CH3, what do you expect its splitting pattern to be? It's a triplet because it has 2 neighbors. And where do you expect it to be? Now it's really far away from that oxygen, so we expect it to be somewhere around 1. In fact, it's even a little below 1 in this case. So one by one, we confirm that all the data is there. We're guaranteed to have the right answer. Well done. Okay, let's do one more. C6H12O3. So what do we do first? Since we don't have an IR to analyze, we'll go straight to the formula. And we'll ask ourselves if it was saturated, the formula would be C6H2N plus 2, that's 12 plus 2. It would be C6H14. The actual formula is C6H12. So we have 2 hydrogens missing. That tells us we have 1 degree of unsaturation. So what does that mean? Our structure has to have a ring, or our structure has to have a double bond. Must have one of those two in order to come up with the right number of hydrogens. Okay, so there's our formula. Now we go to find our pieces. We have a 3 hydrogen signal and another 3 hydrogen signal. That means I have 2 methyl groups. Okay, these are very close to each other, but can you see one is a triplet, 1, 2, 3, and then this one is a doublet. So we can point those out. They're not quite overlapping. They're very close to one another. What other pieces do we have? We have a CH3. You can write them down here, or you can write them up here. Wherever you're most comfortable. Eventually you have to get them kind of close to each other so you can work with them. And then what do we have here? We have a CH. Remember, a CH has 3 arms to make 4 bonds. And then 2 hydrogen signal, we have a CH2. It looks like this is pretty far to the left, pretty far downfield, but notice I'm just showing 0 to 5 here. So this is not, you know, as far down as it might appear. So we have a CH2. Good. Any other pieces? We have 1, 2, 3, 4, 5 carbons, but we need 6, so there's an extra carbon. We need 3 oxygens. And what else do we need? We need a degree of unsaturation. So I think I have an idea of how to consolidate some of these little pieces. What can you do with an extra carbon and an oxygen and a degree of unsaturation? I think we can turn it into a carbonyl with 2 arms. Right, a carbonyl itself doesn't show up in the proton NMR. I'll always hear the protons. So we have to work with the formula to deduce the presence of a carbonyl in this case. But we still have 2 oxygens. Remember, oxygens each have 2 arms. Okay, where do you think those oxygens are attached? What pieces do you think have oxygens on them? Well, we can look down here and we see that an oxygen would cause it to be pretty far downfield, right? So I'm thinking that this methoxy group probably has is a methoxy group. It's a singlet, and it's all the way down past 3. So this looks like an OCH3. And these 2 look like they're attached to an oxygen. We only have 2 oxygens to work with, so we can't put one on every single piece. Okay, but I know those are attached to oxygens as well. So that's something that we can keep in mind. Okay, but to really put things together, I know I have an OCH3, so we can cross those out and make that its own piece. We have a OCH3 group for sure as one piece. And let's take a look at one of these other methyl groups and start building from there. So what do we have for this one CH3 is a triplet. What does a triplet tell you? What piece, here are our pieces, it could be attached to another, well, it can't be attached to another methyl because that's bringing 2 N pieces together. But we could attach it to the carbonyl, the CH, or the CH2. What's it attached to? It must be attached to the CH2. That's what makes it a triplet. Okay, so now we've taken away that piece. We've taken away another methyl. And then let's jump to this second methyl group. This other methyl group is a doublet. What makes it a doublet? This doublet must be next to the CH, just one neighbor. So it has 2 other arms. Okay, so now we're beginning to, now we've come up with some 1, 2, 3, 4, 5 pieces. How can we put these together to have them make sense? Remember we said that this CH2 needs to be next to an oxygen, and this CH needs to be next to an oxygen. So there's a few ways we can put this together. One of them is we can have this oxygen then attached to our CH. And we said this has a CH3. So that way this oxygen is shared both with the the CH2 and the CH, right? So that would take care of all those. And then we have an CH3 and a carbonyl, so the carbonyl must come next. So we could have that. And there's actually one other possibility that would also work in this case, because you have this ethoxy group and this methoxy group. They can be kind of interchangeable. So we could have a CH3 over here, and then a carbonyl, and then the OCH2 CH3. This would not really have much effect on the structure on the NMR, because we would still have the same function groups present and still have the same splitting patterns. Okay, now if we had our tables, we would be able to calculate them more precisely, and it turns out that our correct answer is the one with this methoxy group here. So it's actually the ethyl ester with a methoxy in this position, and you would be able to calculate for this CH2, for example, is this CH2 next to the oxygen of an ester, or is this CH2 next to an oxygen just of a plain ether? So if you were given NMR tables where you can calculate those, you would be able to more precisely approximate that this is coming at 4.2. This is going to be more consistent with 4.2. Okay, but let's confirm the rest of these. Okay, let's label these A, B, C, D, E. I'll put D and E up here. And let's see if we can label them one at a time and confirm that we have the right answer. So A, we have a CH2. We could start with our structure. Sorry, I'm jumping around a little bit. We could start with our structure. So here we have a CH3. What would we predict for this spectrum? A 3-hydrogen signal. It is a splitting pattern. It's a singlet. Where do we expect it to come? What chemical shift? It's next to an oxygen. So that brings it around 3.8. And do we have that? That's right here. It's a little closer to 3.3. So we can modify that. And these are protons C. How about this CH3? What do you expect for that signal? It has just one neighbor, so we expect that to be a doublet. It's attached to an ordinary carbon. Even though there's some groups attached to that, we would expect it to shift a little bit. So somewhere around 1, turns out that it's a little closer to 1.4. So that makes sense. This is a doublet, and so this is peak D. This proton up here has how many neighbors? It has 0 neighbors. And I'm sorry, it doesn't have 0 neighbors. You look at the carbon, I suppose it wasn't making sense. The carbon, what carbons are attached to that? There's 0 neighbors over here and 0 neighbors over here, but this carbon has 3 neighbors, has 3, so that's why we expect that to be a quartet. Luckily, those neighbors showed up, because I'm looking over here, and our 1-hydrogen signal is a quartet, so it must have 3 neighbors. Of course, that means it's attached to a methyl. So this is peak B. Does a chemical shift make sense? Yes, because that carbon is attached to an oxygen, and it's attached to a carbonyl. So we expect that to be pretty far downfield. This CH2 is a 2-hydrogen signal. What is its splitting pattern? How many neighbors does it has? It has 3 neighbors. So this we expect to have a quartet. And what chemical shift do we have attached to that oxygen? We expect it to be about 3.8. An oxygen of an ethyl ester brings even further down, so that's evidence on this structure being the better one. This is going to be A, peak A. And finally, this last methyl group has 2 neighbors, so we expect it to be a triplet. And it's just attached to an ordinary carbon, although there's an oxygen after that. So rather than at 1, we're seeing it at somewhere, where's our triplet? Is this first peak, so 1.3 or so. and that's peak E. Okay, so one by one we can confirm it. In certain cases, if we're not given NMR tables to do precise calculations, we might find more than one possible answer, like in this case. But if we were given those more precise tables, we could really narrow it down to which is the best match. Okay, and let's try this one. C8H18 is our formula. If it was saturated with 8 carbons, what would we expect? We would expect H, so this is asking if saturated, it'd be 16 plus 2, it'd be C8H18. And guess what? Our formula is C8H18. So there are no degrees of unsaturation. That means this molecule has no double bonds, and it has no rings. So it's just a plain old hydrocarbon, with carbons and hydrogens. So what pieces do we have? We have a 1 hydrogen signal. That's a CH. Looks like a multiplet here. Not a multiplet. Looks like there's many, many signals. This is blown up. So a lot of splitting here, a lot of neighbors, but we'll worry about that later. A 2 hydrogen signal means I have a CH2. A 9 hydrogen signal. How do you think we can come up with a 9 hydrogen signal? Must be 3 methyl groups that are all equivalent if they're all coming out to be one nice signal. And how about 6 hydrogens? 6 hydrogens could be a CH2 and a CH2 and a CH2. You know, that would require a lot of molecular symmetry, but a more likely option, and one that's going to work in this case, are 2 methyls, 2 CH3s. Okay, so that's all of our hydrogens. That's 10, that's 18 hydrogens. How about our carbons? We have 1, 2, 3, 4, 5, 6, 7 carbons. But actually we need 8. So another piece to our puzzle. Very important that we check that, because in addition, if we just try to put those pieces together, it's never going to work because we were missing a carbon. Okay, so now let's try and put those together. Our 2, and we can start anywhere. Our 2 CH3s here are a doublet. We have 2 peaks there, so that means they must be attached to this CH. That makes them a doublet. So that takes care of this piece and those pieces. This CH2 is also a doublet. So what does that mean it's attached to? That must be attached to this CH, have just one neighbor. And then these 3 methyls, how do we get 3 equivalent methyls that end up being a singlet to have no neighbors? Well, we'll put them all on this same carbon. Let me draw them separately so we still have our pieces together. Okay, and this can't be a hydrogen because this carbon had no hydrogens on it. It was just a carbon attached to all carbons. And so how do we finish off this molecule? Well, we simply attach the 2 pieces, because those we've already used all of our pieces. So it's this half connected to this half, and then we're done. I can draw it as a line drawing. We have a CH3, CH3, CH, and then a CH2, and then a carbon with no hydrogens on it, but 3 methyl groups. So let's make sure this makes sense. Here we have, we can label these guys A, B, C, D as our 4 different types of protons in this molecule. HA is a 1 hydrogen, I'm sorry, we'll go backwards here just so we can label them. So let's look at this guy first. These 2 methyl groups we expect to be equivalent, so we're going to get a 6 hydrogen signal. What splitting pattern do we expect? It has just 1 neighbor, so we expect this to be a doublet. And notice that all of these chemical shifts, this is 1, I'm sorry that's so small, 1 and 2. All these chemical shifts are very similar coming around 1, because there's no pi bonds, there's no heteroatoms, there's nothing to cause any deshielding. So they all have very similar, the chemical shift isn't going to help us in this case on deciding who gets connected to whom. It's simply based on the splitting patterns. So we expect this to be a doublet, and it is. So where is our 6 hydrogen doublet? Right here, peak D. And what do we expect for this hydrogen? It's going to be a 1 hydrogen signal. And how many neighbors does it have? A lot of neighbors. It has 3, 6, 7, 8. It has 8 neighbors, so it's going to be 9 peaks. It's going to have 9 peaks. Now, take a look at this spectrum, and if you look very, very carefully, you can see actually there's a little bubble down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can maybe see those. In all likelihood, you're not going to be able to see those, but you can see how tiny, how shallow that peak is, because there's only 1 hydrogen accounting for it, and it's spread out, the area is spread out over those 9 peaks. So they're all going to be extremely short and small, and those satellite peaks, those end peaks, are probably going to be indistinguishable. But you just would have to trust that there's many peaks there, even if you can't number them all, even if you can't pick them all out. Okay, so that's good. So that's peak A, that's signal A. How about this CH2 would be a 2 hydrogen signal. And how many neighbors does it have? No hydrogens on this carbon and 1 hydrogen on this carbon, so we expect it to be a doublet. Sure enough, we have a 2 hydrogen doublet right here, signal B. And then finally we have all 3 of these methyls are equivalent. So we have a 9 hydrogen signal here. And then that's going to be, we take a look at how many neighbors, and here's the carbon they're attached to. This has 0 hydrogens on it, so that's going to be just a singlet. No splitting at all for those 9. And where do we have a 9 hydrogen singlet? Right here, peak C. Okay, so bit by bit, we're going to determine our pieces. We're going to start to put them together. Eventually, we're going to come up with a complete structure, a complete molecule.